In this video, we're going to look at proof by induction. You've probably come across proofs before, and what you've probably come across is a direct proof. So that means we start with a statement, we do steps until we arrive at the thing we're trying to prove. Now we're going to look at another proof, which we call proof by induction. Proof by induction follows 4 steps, and it's important to include each of those steps. So, step 1, we need to show that the general statement's true when n is 1. Step 2, we assume that the general statement is true for n is some number k. Step 3, we show that if it's true for n is k, then it's also true for n equals k plus 1. So we're showing that it's true for the next one. And step 4, we write a conclusion. So we can deduce that it's true for all positive integers n. It's important, or with this kind of proof, in order to use this kind of proof, we generally need to be fairly sure that the thing we're trying to prove is actually true. And just a word about answering exam questions. You need to write a conclusion and indicate clearly what you're doing. So you will not get full marks for the algebra only with no explanation or conclusion. So let's look at an example, and we'll look at an example with sigma. So we're going to prove that the sum of the first n odd numbers is equal to n squared. So this is what we need to prove down here. So sigma 2r minus 1 from 1 to n is equal to n squared. So let's look at our 4 steps in turn. So step 1, show that the general statement's true for n is 1. So this is our general statement, and we're showing that it's true for n is a member of all the positive integers. So let's try with n is 1. So we can write that down. Well, the right hand side, which is this, is 1 squared, which is 1. The left hand side, which is this, is 2 times 1 minus 1, which is also 1. So hence, the statement must be true for n is 1. So we've done our first step. So let's go to our step 2. So assume that the general statement's true for n equals k. So this is our general statement here. And let's assume it's true for some integer n equals k. So we've got another statement down here. So sigma 2r minus 1, which is 1 plus 3 plus 5, etc., is equal to k squared. Now step 3 is where we do all our algebra. So we need to show that it is then true for n equals k plus 1. So the next term is n equals k plus 1. So we've got our left hand side. So we're now going from 1 to k plus 1. And our right hand side, well, the first bit is up to the first k, and then we've got an extra one now, so plus 2k plus 1 minus 1. So this is what we're going to try and show. So the way we can do that, we've got the first part of the sum, which we already know, which we've already looked at. So we've assumed that this is true. So we've assumed that this is equal to k squared from our step 2. We've kind of got an extra term here, so up to k plus 1. So we've got the sum up to k plus 1 must be equal to k squared plus 2k plus 1 minus 1. Now simplifying that a little bit, we've got k squared plus 2k plus 1, and that can be simplified again to k plus 1 squared. So we've now shown that if it's true for n is k, then it's also true for n equals k plus 1. So we've got this down to k plus 1 squared. So next step is step 4. All we need to do now is write a conclusion. So we can deduce that it's true for all positive integers n. So if the statement's true for n is k, then we've shown that it's also true for n equals k plus 1, which was shown in step 3. Since it's true for n equals 1, which was shown in step 1, then we can conclude that it's true for all n is a member of the positive integers. And that's our proof by induction.